Today I will review math questions for your final exam. Okay, I will go over four math questions. Okay, three from linear kinetics chapter and one from angular kinetics chapter. Okay, let's start with the linear kinetics math questions. Okay, IP number 5, introductory problem number 5. Okay, there is a football player here. A football player pushes a 670 Newton blocking sled. The coefficient of static friction between the sled and grass is 0.73, and the coefficient of dynamic friction between the sled and grass is 0.68. Okay, this is larger than this. And then there are three questions in this IP5. Number one is A. How much force must the player exert to start the sled in motion? If you take a look at hint here, this question is about maximum static friction, which is a force required to initiate a motion or start the motion. Okay, for this question, you need to use a static friction coefficient. And the next question is, how much force is required to keep the sled in motion? If you take a look at hint here, the concept is about kinetic friction. So in order to solve this question, B, you need to use the friction coefficient of dynamic friction. Okay. Now, according to the friction formula, you can quantify friction by multiplying mu by normal reaction force. Okay. So let's calculate the maximum static friction first. So mu for maximum static friction should be coming from here. Static friction 0.73 times normal reaction force. Okay, so you can get this from the weight of sled here. Okay, weight of sled. Okay, this one will be used as normal reaction force because the weight of sled is acting downward due to gravity. If then we will get the same amount of force coming from the ground to the sled. Okay, that's why this one 670 will be used as normal reaction force. So simply multiply these two. If then you will be able to calculate maximum static friction. Okay, and then for the B, to calculate the kinetic friction, this time we need to use this dynamic friction coefficient instead of using static friction coefficient because we need to calculate this time kinetic or dynamic friction. Okay, normal reaction force remains the same. Okay, the weight of this sled, and so simply multiply these two. Okay, if then you will get the kinetic friction, the value here. Let's compare this value. So this maximum static friction value is larger than kinetic. And then one more question here. Okay, answer the same two questions, previous two questions, with the 100 kilogram coach standing on the back of the sled. Okay, we have here additional weight to measure here, but I want to take a look at the unit of this the coach. Okay, weight of this coach is given as a kilogram, right? This is actually not weight, but his body mass. So that in order to solve this problem, you need to convert this body mass to the body weight by simply multiplying this value by 9.81 because we need actually force value, not the mass value. Okay, there is hint here. The normal reaction force must be computed first. And the normal reaction force between the sled and grass comes from weights of the sled and coach. Here, weights, right? Not the mass. That's why we need to convert this body mass to body weight. So we got this equation for converting body mass to body weight. So body mass here, to simply multiply this one by 9.81, which is a gravitational acceleration. Okay, if then, so we can convert the body mass of 100 kilogram to the body weight of 981 Newton. Okay, and then add this one to the weight of sled. If then total normal reaction force will be 1651 Newton. And then you can use this one as total normal reaction force. And then do the same step as the previous the questions. So here to calculate the maximum static friction with these two systems, okay, still friction coefficients remain the same. So static friction coefficient here and dynamic friction coefficient here, and multiply these two to calculate maximum static friction, and then to calculate these two to calculate the multiply these two to calculate the kinetic friction. And then the second question from linear kinetics chapter is about the linear momentum conservation. Again, here we have a lineman again, okay, football situation. The lineman A has a mass of 100 kilogram, and he's traveling with a velocity of 4 meters per second. When he collides head-on with the lineman B, who has a mass of 90 kilogram, and he's traveling at 0.5 meters per second. If both players remain on their feet, what will happen? Again, this question is about linear momentum conservation. And then there's a hint here, one more hint. Collides head-on means the players are moving in opposite directions. Okay, they are moving in opposite direction. And then we got here mass of lineman A, and then his velocity 2, and then mass of lineman B, his velocity 2. If then we will be able to calculate linear momentums of two players. We simply multiply mass times velocity. So this situation can be visualized something like this. Okay, player number 1 and player number 2, and his body mass, his velocity, his body mass, and his velocity. Okay. Then let's, according to linear momentum conservation, okay, as you learned, the linear momentum before collision must be equal to linear momentum after collision. Okay, so keep that in mind. Right here, step 2, compute the total momentum before collision. Okay, this is total linear momentum before collision. Here, so m1, which means momentum due to first player, and m2, momentum due to the player B, second player. And then multiply his body mass by velocity here, mass times velocity. That will be 400 kilogram meter per second. And then momentum coming from the player 2. His body mass and then his velocity here, and then negative 405 kilogram times meter per second. This is negative, right? Because he is moving in a negative direction. Okay, so we define this way positive, and the other way is a negative. That's why. And then add them up, add these two. If then total linear momentum before collision will be a negative 5 kilogram times meter per second. And then lastly, compute the total linear momentum after collision. After they collide with each other, as you learn, they will move together. They will become a single unit. That's why we have to add these two body mass, okay, 190 kilogram. And then this one, okay, value must be equal to this one. So we can simply apply the linear momentum conservation, as I explained earlier. So momentum after collision must be equal to momentum before collision. So you can divide each side by 190. If then the answer will be negative 0.03 meters per second. It's negative, which means they will move together to the negative direction. So answer could be something like this. Player B pushed player A with a velocity of 0.03 meters per second, which means they are moving together in the negative direction. Again, this is a question about linear momentum conservation. And then the next question is IP number 9. Okay, so we went over the similar questions of this one to the question in the slide actually, but again we will do this one again. There's stairs here. Okay, stairs here. This is asking us about calculating the mechanical work, power, and energy. Okay. There's stair here, a set of 20 stairs, and each of 20 centimeters height is ascended by a 700 Newton man in a period of 0.5 seconds. Okay. Calculate the mechanical work, power, and change in potential energy during the ascent. Okay. As I mentioned earlier, this is a concept of mechanical work, power, energy. Okay, in order to calculate mechanical work, mechanical work is force times displacement times cosine theta. So we need to calculate the vertical displacement first, to calculate mechanical work. So when working against gravity, consider the vertical direction, vertical displacement only, which means the angle between force and displacement is equal to 0 degree. So cosine 0 will be just 1. So don't have to worry about the angle here. So height here, how many stairs here? 20 stairs. And then 20 centimeters is equivalent to 0.2 meters. So 0.2 meters per stair. So multiply this to 4 meters. Total displacement traveled is 4 meters. And then force was 700 Newton. And multiply these two. Force times displacement times and 1. Cosine 0 degree is 1. So 2800 joule here. And note that if you exert more than 700 Newton, the man accelerates, causing increasing kinetic energy. So 700 Newton was used here, assuming no change in kinetic energy. Again, there is one assumption in this question, which means there's no change in kinetic energy. He didn't accelerate while ascending. And step 3, compute the mechanical power. So once you calculate mechanical energy, you can easily calculate mechanical power too, because we got the time information given here. So 12.5 seconds. So once you get the work calculated, simply divide this value time elapsed from top to the top of the stairs. Then the answer will be 224 watt. The unit of power is watt. And lastly, you have to compute the change in potential energy. As I mentioned earlier, there will be no change in kinetic energy in this question. So they just compute the change in potential energy. Let me give you a hint here. The concept is work causes change in energy. And change in energy means, as you learn, change in potential energy and change in kinetic energy. So, but here, according to assumption here, the change in kinetic energy will be 0. If then you just calculate the change in potential energy in this question. So this can be gone. And what we have only change in potential energy. And change in potential energy actually equal to the total amount of mechanical work done. This is right here. Because of this relationship, work causes change in energy. But we have only change in potential energy. That's why this mechanical work value will be the same as the total change in potential energy. Okay, the last question is coming from angular kinetics. This is a diving example, and this question is about angular momentum conservation concept. So we have diver here. A 50-gram diver in a full level position with the total body radius of gyration with respect to her transverse principal axis equal to 0.45. This is a rate of gyration is provided, and then his body mass is provided. He leaves a springboard with an angular velocity of 6 revolutions per second. His angular velocity is also provided. And what is the diver's angular velocity when she assumes a stuck position, reducing her rate of gyration to 0.25 meters? Now she reduced her rate of gyration by changing her position from layout to tuck. So her initial rate of gyration was 0.45. She reduced it to the 0.25. Then what is the angular velocity at this position. Again, as I mentioned earlier, this is a concept about angular momentum conservation. So angular momentum remains constant, although she changed her posture from layer to top. This one remain constant. Mass times gyration squared times angular velocity remain constant. Let's calculate her angular momentum for the layer position first. Okay, so again, her mass times gyration squared is coming from here times her angular velocity at the layer position. The answer will be 60.5 kilogram times meter squared per second. And then step 2, compute angular velocity for the top position based on the constant angular momentum. Again, since she is in the air, angular momentum must remain the same. Okay, so again, we got this one from previous step. Okay, and then her body mass, and then her rate gyration at the top position, okay, 0.25 squared, times the angular velocity. This is the variable interest, okay, that we want to calculate. Okay, and equal to angular the momentum, which is calculated from previous step. And if then you can simply divide this value by 50 times 0.5 here, 0.25 squared, which will give you 1944 radians per second. Again, this is a faster than previous angular velocity because she reduced rate gyration, which eventually increased the moment of inertia. That's why she got faster angular velocity at the top position. Okay, this is the end of this math review slide. I really appreciate your participation and then your classroom ethic. Okay, although we got some situation due to the coronavirus, I really tried to do my best to deliver my idea, my lecture through this online. But I hope this online class should help you to better understand the biomechanics and linear or angular kinetics. Okay, thank you.